Okay, so in the last class we were discussing about the construction and working of energy meter. Now we will get a bit more further, mainly about the energy meter constant. Okay, so what is meant by energy meter constant? We have seen that depending on energy, we will have the number of revolutions, right? So this we have understood in our last class. Depending on how much energy it is utilizing, you will have the number of revolutions. So the number of revolutions, the deflection means again it comes in terms of what number of revolutions. So number of revolutions will be proportional to energy consumed in the circuit. Okay. So with that understanding, normally for a meter we define an energy meter constant. Energy meter constant means the number of revolutions made by the disk, made by our aluminum discs, made by the disk in order to indicate 1 kilowatt hour energy consumption. In order to indicate 1 kilowatt hour energy consumption, or we normally call it as what, 1 unit of energy. Okay, in electrical engineering we normally say whenever 1 kilowatt hour is used, we say that it is equivalent to 1 unit of energy. So energy meter constant mean that is the number of revolutions made by the disk in order to indicate 1 kilowatt hour energy consumption. Okay, so that's about the energy meter constant. Based on that, we will have problems to solve during examination. So if I tell it is number of revolutions to indicate for 1 kilowatt hour, it means that the unit of the meter constant, we normally say it is represented in revolutions per kilowatt hour. Revolutions per kilowatt hour. The unit of energy is what? Kilowatt hour. Okay, kW hour. So or watt hour, the power into second. So unit of this meter constant is revolutions per kilowatt hour. Okay. Now let us try to solve one problem. We can find similar problems later. Let us say we have a declared constant declared constant for an energy meter, and the declared constant is of a 5 ampere 220 volt. Okay, 5 ampere 220 volt energy meter we have, and the meter constant is 3275 revolutions per kilowatt hour. 3275 revolutions per kilowatt hour. Okay. So if this meter is subjected to a full load, if let us say this meter is subjected to full load. Okay, meter is subjected to full load for 1 hour. Meter is subjected to full load for 1 hour, and that is a condition. Now let us say that what I am asking is, let us find out what is the speed of this disk. What is the speed of the aluminum disk? Okay, what is the speed of the aluminum disc? That is what I am asking. So in that case, how can we find out the speed? You are aware that the rating of this machine is what? 5 ampere 220 volt. So under full load means it will be taking this 5 ampere 220 volt, and it is running for what? For 1 hour. So that is why my energy is power into time, and here power you can find easily because it has given as full load. So 220 volt into 5 ampere, that is will be my power. 220 volt into 5 ampere, that will be what? That will be my power. And for how much time? For it is running for 1 hour. So with that, if I find out this thing like this, then I will get that the total energy consumed will be 1.1 kilowatt hour. Total energy consumed will be 1.1 kilowatt hour. Okay, so the energy consumed here, you will find it as equal to 1.1 kilowatt hour in 1 hour. Now let us find out how much number of revolutions will be there. Okay, how much number of revolutions will be there. When I say meter constant, you are aware that for 1 kilowatt hour, it will have 3275 revolutions. So for 1.1 kilowatt hour, it is going to have 1.1 into 3275 revolutions. So that is how, if I calculate this one, you will get it as 3602.5 revolutions. Okay, 3602.5 revolutions are needed for whenever it is running at at its rated load condition. So in that case, now you have how what 3602 revolutions happen. That happened in 1 hour. That means 1 hour means 3600 seconds, right, or 60 minutes. So with that you can find out speed in any units. I am going to take the speed in what revolutions per second. In that case it is going to be equal to number of revolutions means 36 power to 2.5 seconds divided by number of seconds for 1 hour means it is going to be equal to 3600 seconds. So approximately I can write that this is equal to 1 revolution per second. Okay. So you can have a problem, different kind of problem. Sometimes it might be giving you like whenever you are connecting a particular load, you are getting this many number of revolutions, and then find out what the meter constant. You can do that. Practice more problems from textbook. So that is the way to do that. Okay. Now one more thing that I want you to look into a bit more. There is something called as creeping in an energy meter. Creeping means under no load condition, whenever let us say you have a no load condition for energy meter, even under no load there will be a slow rotation. Even under load up there is a slow rotation of our aluminum disc. Okay, let us say it was rotating. Now whenever it is not having any friction, anyhow it will be rotating. Even if you release the load, still it will be rotating. That tendency will be there. So, but that is why under no load there will be a slow rotation of the aluminum disc. Slow rotation of what? Aluminum disc. And the system cannot think that okay it is rotating without a reason or there is no load on the system. Still it will be counted as the number of revolutions. So this is called as what? Creeping. So this phenomena is called as creeping, and creeping is an issue because your meter is going to show more energy than utilized. Your meter is going to show what the more energy or more utilization than you really utilized. So that is an issue with the creeping. That is an issue with the creeping. So how can we avoid that? What is done, I will say, you have find it out for yourself that how it is really affecting it. Okay, it is normally reduced by let us say whenever you have an aluminum disc, they will create two holes in the diametrically opposite sides, and whenever you are placing these two holes on diametrically opposite side, then you can avoid creeping. Okay. What is going to be the mechanism behind this? Look out for yourself and understand why this is going to resolve this issue. How this is going to resolve the issue of having creeping for an energy meter. So this is how it is avoided by keeping two diametrically opposite holes on your aluminum disc. Okay, so that's about energy meter as such. What I urge you to do is that do more problems. Don't leave it only up to this problem. Okay, this is a special kind of a problem, but there are more. You can find more problems in your textbook. So do that properly. Now, apart from this, let us see some more thing about our wattmeter or energy meter connections. Okay. We have discussed it already. I am going to talk about wattmeter and energy meter connections. Okay, connections means whenever we are measuring energy, taking the measurement for with wattmeter energy meter, I am going to take both of them together because both of them will have what? These both of them are having two sets of windings. Okay, two sets of winding. And whenever I am connecting it, let us say I have to measure my power through a normal circuit like this. Let us say I have to measure my power in a normal circuit like this. So this is my V of t, and this is my I of t, and this is my energy meter. Okay. Now there is a normal way of connecting it. Let us say if it is like a single phase circuit and we have a single phase energy meter or wattmeter. Normally for a wattmeter you will have terminals like M, L, C, and V. You will pass the current and you will take the voltage reading. In this case, you can short circuit what M and C, so that this is going to measure the voltage across these two terminals. So this is one normal connection I think you have already done in your lab. Okay. But there is an issue. For energy meter, it might be E1, E2 or P1, P2, C1, C2 or P1, P2 terminals, but it does not make a difference. The thing is that depending on how we are making connections, like if at all you are making the current pass through L to M, now it is what M to L your current is flowing. If at all you are connecting it like L to M and C to V is kept the same way, then this wattmeter, you are aware that it has got a dial like this and it starts from, let us say, 0 to 1000 watts. Okay, then it can give you a reading. But interestingly, whenever you are changing this connection, like you have disconnected it and you have connected, like coming from L and then this way you have connected, then your wattmeter is going to show a negative reading. Then what? Your wattmeter will show a negative reading. So that is an issue with wattmeter. And anyhow, you're aware that wattmeter cannot go to this negative side. And in your measurement lab, you might be doing the 2 wattmeter method, or you might have encountered this. And that time we will interchange the terminals. Okay. But in a normal, whenever you are using a wattmeter, normally they will be provided with enough markings, or it is common sense to understand what is meant by M, L and CV. We will connect the M side to the mains and the L side to the load side, and C is normally taken as a common and V to the other terminal. So this way, this problem is there, like it can have wattmeter energy meter, they can have a negative reading. In case of an energy meter, if you the same way you have got what 2 sets of wires, or you have got a current coil as well as pressure coil. If at all it is not connected in the normal way, negative reading means here your aluminum disc will rotate what in the opposite direction. If at all your aluminum disc was rotating this way, now once you are changing the connection, then it will rotate in the opposite direction. So that issue is there. So you should take care on how we are connecting a wattmeter or energy meter. Now, apart from that, now let us discuss a little bit about the 3-phase power measurement. Okay, 3-phase power measurement. We have seen single-phase power measurement, but now let us discuss 3-phase power measurement. Okay, 3-phase power measurement means, first of all, in three phase what it is meant that you have got 3-phase can be 2 types. It can be either 3-phase 4-wire connection, like you will have 3 phases and 1 neutral, or it can be 3-phase 3-wire connections. Okay, you will have only 3 phases connection there. So these 2 types of connections can be there. And for measuring measurement of 3-phase power, we can adopt a method called as using 2 wattmeter. Okay, we have a method for 3-phase power measurement, which is what the 2 wattmeter method. 2 wattmeter method. Let us see how it is implemented. Okay, let us see how it is implemented. So for that, consider that you have a 3-phase load. For now, I am going to consider it as a balanced load. Let us say I have a 3-phase load like this. Balanced or unbalanced, it does not make much difference. So I have a 3-phase load like this, and it is given we will take we will have power coming from the source. Okay, now I will have 2 wattmeter. One I will keep it like this and connect it, and another one I will take. Okay. Now let us suppose that this is the R phase, or I will use A phase. This is the A phase, then this is B and this is C. Okay, and similar to A, you will have one more wattmeter, and that wattmeter I will connect in C. Okay, that wattmeter I will connect in C. Okay, so this is my connection. Now I have the last phase, which is what B. So in this thing, what I will do is that the connections are like this. Connections are, first of all, this will come here. Then M and C, or you can say C, if it is C1, C2 and P1, P2, then C1 and P1 are short circuited, and this I will connect to the B phase. Similarly, from here also I will take a connection to this phase. Okay, and these are my phases A, B and C. Okay, so this is how we will have 2 wattmeters connected in order to measure 3-phase power. So this is my wattmeter 1, W1, and this is my wattmeter 2, W2. Now let us see how it is going to measure the 3-phase power. Before that, I think you are aware of the 3-phase power. What is the equation for 3-phase power? 3-phase power is given by root 3 times VL IL cos phi, where VL and IL are the line voltage and line current, or otherwise I can write it as 3 VPS IPS cos phi, or where VPS and IPS are what? Nothing but the phase voltages and phase currents. So this is the normal equation for the three-phase power measurement, I think, which you are aware of. So now, how this W1 and W2 measurement are going to give you what? Give you the three-phase power measurement. In 2 wattmeter method, we will make the connection as such as you are seeing now, and here if at all you measure the W1 plus W2, or if at all you add the two wattmeter readings, then you will get the total watt power. It will be equal to what? The total three-phase power. Now let us discuss how it is possible. So now you are aware that IA means the time dependent current in the A phase, or the VA, any way you can take. Okay, I will take VA of T. The voltage in the A phase is given by Vm sine of omega T, right? Omega T. So that is my reference. VA sine omega T. If at all it is true, then the voltage in the B phase means A to N, and this is what B to neutral means, the second phase to neutral voltage, that will be given by Vm sine of omega T minus 120 degree, right? And the Vcn of T, that is given by, or the phase voltages these are, Vm sine omega T minus 240 degree. So this is true. This thing is something that you are aware of, right? So these are the voltages. Now, if we represent that in the phasor domain, I am going to draw VA like this. Okay, I am going to draw VA like this. Then from VA at 120 degrees, with what? Negative 120 degree, I will have my B phase. They will all be having equal magnitudes. If it is not so, that is just because of my drawing. Now I will have what? Another quantity, which is what? The C phase. Okay. So this is VC, or which means that A to neutral, or these are the phase voltages. Okay, so that this is true. Now depending on load, I will have what? The current as well. Depending on the load, I will have a current, and these are impedances, so that the current can be what? Let us take that the current is lagging. Let us say the current is what? Lagging. Current is lagging means I will have my currents. A bit what? Lagging. Okay, I am going to show that lagging part here. So this is what I am going to draw as. This is what I am going to draw as my IA. Okay. So from that, similarly, I will have what? Fixed by, if in a balanced load, I will have what? Similar thing in VB and VC. So this is my IC. So these three currents are there like this, at an angle of how much? At an angle of phi. So this angle is phi. So this is true. Now let us find out what these wattmeters are measuring. Normally the wattmeter W1 will give you a measurement of power corresponding to what is the current coil? Current coil is carrying a current of IA, and the voltage in between what? A and B. Just connected, the C and B are connected between A and B. So this voltage is how much? VAB. So the wattmeter is going to give you a reading equal to VAB into what? IA. The current carried by the current coil, the whatever be the voltage we are applying between the pressure coil, is equal to VAB, and what? The cosine of the angle between voltage and that current, VAB and IB. So that is what my first wattmeter reading is going to be. So wattmeter W1 reading is what? VAB into IA into cosine of the angle between what? VAB and IA. Let us see what is VAB here. If at all we have VA here and VB here, then VAB, from this phasor diagram we can find out. So VAB will be equal to VAB will be equal to what? VA minus VB. That is what is VAB. So we have already got VA here. For minus VB, VA, or I can write it as it is equal to VA plus minus VB. So for minus VB, what I should do? I should draw it in the backwards direction. Right. So this is what? This is my minus VB. Now if I add VA and minus VB, I will have what? Using parallelogram law, I will have my total VAB. So this is what? This is my VAB. Okay, this is the VAB. And now you can see the angle between VB and minus VB is how much? 180 degree. And the angle between VA and VB is 120 degree. So from that you can understand that this angle is going to be how much? This total angle is going to be 60. That is why this angle is going to be 30. Clear? So VAB and VA will have an angle of 30. But here in my equation, I needed the angle between VAB and IA. So the angle between VAB and IA will be 30 plus what? Plus 5. So this so I can write it as W1. I can write as VAB into IA into cosine of what? 30 plus 5. So that is my W1. Similarly, I can find out W2. Okay, similarly what? Similarly I can find out W2. What will be W2? You can see here. So here you can see W2 means it is here. So the measurement will go like this, and W2 you can write as the voltage measured is how much? VCB. Matter is VCB, so it is VCB, and the current carried by is what? IC. VCB into IC into cosine of the angle between what? VCB and IC. If I apply that here, that is going to be equal to what? VCB into IC into cosine of the angle between them. What is that angle? Now for that we should find out VCB. VCB is VC minus VB. So VC is here and VB is here. So my VCB will be equal to VC plus minus VB. So minus VB I already have. So with that, if I make the next parallelogram here, I will get what? I will get my VCB. I will get my VCB. Right. Right. So here you should understand this also is how much? 5 only, and this total angle here, that is what? 30 degree. Okay, take your time to understand that, so that the angle between VCB and phi is going to be 30. The total angle is 30, so 30, and this much is 5. So this is going to be almost 30 minus 5. So W2 is going to be equal to VCB IC into 30 minus 5. For a balanced load, this VAB and VCB magnitudes are going to be same. IA and IC magnitudes are going to be same. They just become the line voltages or what? The line currents or the phase voltage or the phase currents. So based on that, I can write this as what? Simply I can write it as what? VL into IL into cos 30 plus 5. And this will be VL IL into cos 30 minus 5. Now I have already told you that whenever I am measuring W1 plus W2, it is going to be equal to the three-phase power. So let us prove that here. So now if I add VL IL into cos 35 plus 5, right? That is W1 cos 30 plus 5 plus VL IL into cos 30 minus 5, that is W2. If I add both of them together, then it will become VL IL into cos of 30 plus 5 plus what? Cos of 30 minus 5. This is going to be equal to what? This is going to be equal to VL, it is cos A plus B plus cos A minus B. So I will get it as what? 2 times cos of what? Cos 30 cos 5. Right. So this I can write as VL IL into 2 into how much is cos 30? Sin 30 is 1 by 2. So cos 30 is how much? Root 3 by 2 into cos 5. 2 and 2 will get cancelled. So I will have root 3 times VL IL cos 5. So now we have, I have what? The W1 plus W2, that I have got as what? The three-phase power. Right. So this way I have wrote that W1 plus W2 is going to be equal to the three-phase power consumed in the load. If I change the line voltage value, since it's a star connection, line voltage value if I change into phase values, this will become what? VL will be root 3 times VPH. So that is why this will become 3 times 3 VPH IPH cos 5. So this all are same. So using 2 wattmeter method, you can find out the three-phase power. That is what I want you to understand. Now, just for curiosity, let us find out W1 minus W2 also. Anyhow, I am measuring W1 and W2, right? That is the direct reading I get. So W1 minus W2 is going to be equal to, it is all the same, right? So minus W2 is going to be equal to VL IL into cos of how much? 30 plus 5 minus cos of 30 minus 5, right? So this is going to be equal to VL IL into 2 times of what? 2 times of cos 30 into what? Sine 5, sorry, sine 30 into sine 5. So that is why this is going to be equal to VL IL into what? Sine 5. This is going to be equal to VL IL into sine 5, right? Now W1 minus W2 I have got as VL IL sine 5, and W1 plus W2 I have got it as what? The root 3 times, okay, root 3 times VL IL of what? Cos 5. Now if I take W1 minus W2 divided by W1 plus W2, that is going to be equal to what? VLIL, and VLIL will get cancelled. So this one is going to be equal to root 3 times, am I right? Yeah, this is one is going, not root 3 times, this one is going to be equal to what? Tan 5 divided by root 3, right? Or I can write that tan phi is going to be equal to root 3 into W1 minus W2 divided by W1 plus W2. Now from this you can find out phi. Phi will be equal to tan inverse of this equation. So now whenever you are having a 2 wattmeter method, you have an indirect way of measuring what is the power factor. What is the power factor angle you can indirectly measure using a 2 wattmeter method. Okay. Now, so this is what I want you to understand here. This equation is important, and you should also understand that you can measure what 3-phase power using what 2 wattmeter method. Instead of this, you can also try using this what 3 wattmeters placed on each of the phases with respect to neutral, and add all these things up in order to get what the 3-phase power. That is not an issue. So that also you can do. No problems with that. So that is possible, but this way we can do, and we can measure the 2 wattmeter method. We can use a 2 wattmeter method even in a 3-phase 3-way connection to have the 3-phase power measurement. Now for your understanding, let us say my power factor angle is phi. Power factor is something, and what the relationship between W1 and W2. Relationship between W1 and W2. Let us find out. Whenever my power factor, let us say, is 0 degree, okay, not power factor, phi is 0 degree, it means that voltages and currents are in phase, or what the power factor is going to be 1. Now if you apply this thing here, what will be tan phi you can identify. That is how you can find that your wattmeter reading W1 and W2 should be equal. Then only this W1 minus W2 is going to become 0, or that in turn will tell you that you will have tan phi equal to 0. Understood? So this is where you can find that W1 will be equal to W2 whenever you have unit power factor. Whenever it is a unit power factor system, you will have what W1 will be equal to W2. Let us say it is 30 degree. Let us say what phase difference is 30 degree. It means that a power factor will be 0.866. In that case, whenever it is 30 degree, you will find that W1 will be equal to 2 W2. One will be the double of the other one. Okay. Now, whenever it is 60 degree, power factor, as you are aware, it will be how much? 0.5. That time, there is something interesting will happen, that your first wattmeter, W1 itself, will show the total power, and the second wattmeter reading is going to be 0. So whenever it is 60 degree, you will have 1 wattmeter of how much? 0. Now let us say that you have 90 degree or a completely leading or lagging load. In that case, you are aware that the phase power factor is how much? 0. When power factor is 0, what it will imply? Power factor is 0 means your total power should be equal to what? We are measuring real power, so the total power should be equal to 0. That is only possible when your W1 is going to be equal to minus W2, or one of your wattmeter is going to show a negative reading, and that is why you will interchange one of the terminals of the current coil to get the measurement you seek. Okay, that whatever reading you get, then you will take it as what? A negative value. So wattmeter can show negative reading whenever you have a completely lagging or leading load. I am not saying that this is the only possibility of having a negative load. Whenever your reading is more than, whenever it is lagging or leading more than 60 degree itself, you are going to have what, a negative reading. And whenever it is 90 degree, then your wattmeter 1 and wattmeter 2 should be having the same reading, but in the one will be the negative one. Okay. So that is, this you should understand. Okay, this is your understanding. Work it out. If at all you need time, so then take the time and work it out, this thing.